In this video, we want to have a look at reduction of carbonyls to alcohol. There are several means of preparing alcohol, and I'm going to list some of them over here. So preparing alcohols. Now we can do that by synthesis from alkenes. We can also do that by reduction of carbonyls. We can also do nucleophilic addition. Nucleophilic addition, that one involves Grignard reaction and organolithium reagents, and we can also do nucleophilic substitution of alkyl halides. Nucleophilic substitution of alkyl halides. Alright, so for carbonyls are mainly compounds with the characteristic carbon which is doubly bonded to oxygen. So we have some carbonyls that can be reduced. Now we can reduce aldehydes. Now aldehydes have the R, which is the alkyl group, and a carbon doubly bonded to oxygen and hydrogen. And we also have ketones. Now the ketones is just like the aldehyde, but then we have another R group instead of the hydrogen. Alright, and then we also have carboxylic acid. Carboxylic acid. Now they have the R group bonded to carbon, which is doubly bonded to oxygen, and we have OH. So that is carboxylic acid. And we also have esters. Now for the esters, we have R, carbon doubly bonded to oxygen, and then we have OR. Alright, so these are the carbonyls that we can reduce to alcohol, and to reduce these we need reagents. We need some reagents, and the reagents that we can use in doing this, we have, so I'm putting here reagents. We have sodium borohydride, sodium borohydride, that is NaBH4 in acid. So I'm just going to put H plus for acid, or say water. Now we can also use lithium aluminium hydride, lithium aluminum hydride, that is LiAlH4. And we can also complement this with acid, or we can use THF. THF is tetrahydrofuran, THF, or we can use Et2O, that is diethyl ether. So we can use these two as reducing agents. And one more, we can also do catalytic hydrogenation with hydrogen gas, or we use metals like nickel, platinum, palladium, or what is commonly known as Rene nickel. So these are the main reagents that we can use to reduce carbonyls to alcohol. Now, what you need to take note of is that sodium borohydride is a weaker reducing agent compared to lithium aluminium hydride. And so when it comes to the carbonyls that we can reduce using sodium borohydride, we have aldehydes and ketones. So for aldehydes and ketones, we can use sodium borohydride, NaBH4, and then for lithium aluminum hydride, it is a stronger reducing agent compared to the sodium borohydride. So we can use lithium aluminum hydride to reduce all of this group, even including amides. Alright. So right now, another thing we need to take note of is the fact that when we reduce aldehydes, we get primary alcohols. So aldehydes will give us first degree alcohol. That means that we're going to have the OH group at the terminal, and then if we reduce ketones, we get secondary alcohols. So ketones will give you secondary alcohol. Alright, so let's look at the mechanism involved in using sodium borohydride to reduce a carbonyl to give you an alcohol. Alright, so I'm going to put here sodium borohydride. Now in sodium borohydride, we have the boron bonded to 4 atoms of hydrogen, and the name hydride should make you know that the hydrogens have a negative charge. And so we have the sodium, which is positively charged, to balance it. So this is the structure of the sodium borohydride. Now, when we have hydrogen being added to a compound, we call it hydrogenation or reduction. If we are taking hydrogen out, then that is oxidation. In this case, we are reducing, so what is going to happen is we'll have the hydrogen being added to our organic compound. Now, there are 2 main steps involved in this reaction. Firstly, we are going to have the hydride, which is H minus, attacking the carbonyl. So let's say attacks the carbonyl carbon, and this is going to give us alkoxide. Then we'll have the alkoxide ion protonated by a dilute acid. So let me put that here, alkoxide protonated by dilute acid. Alright, so in this example, I'm going to use benzaldehyde. So we have benzaldehyde, the aromatic benzene, And then we have the carbon doubly bonded to oxygen and hydrogen. And so the first thing that is going to happen is we'll have the hydride attacking the carbonyl carbon. Now the hydride, we have BH4. Remember, the hydrogen bears the negative charge. Now this is because the hydrogen is far more electronegative compared to the boron, so it bears the partially negative charge. So this is we are going to use this curve arrow from here to the carbon, and it's going to kick off one of these bonds, dropping its electrons on the oxygen, and this will give you the alkoxide. And so we have the benzene ring again. Then we have the carbon, but this time a single bond to the oxygen with 3 lone pairs of electrons and then a negative charge. Then remember the hydrogen coming from the reducing agent, so we have 1 hydrogen here, and the initial hydrogen that was on the carbon atom, so this hydrogen here. Alright, so now that we have the alkoxide intermediate, what is going to happen is that is when the acid comes in. So I'm going to put an arrow here, the acid, which is going to be H3O plus. So we have oxygen triply bonded to hydrogen, and hydrogen here with a positive charge. Now this oxygen has a lot of electrons and a negative charge, so the arrow is going to move from the oxygen to the hydrogen, and we have the alcohol. So we have the benzene ring, the carbon, this time with the oxygen, 2 lone pairs, and a hydrogen attached, and then we have the resulting hydrogens attached to the carbon. So this is your alcohol. This is what you form from this reaction. That means that we can have a byproduct, which is water molecule, which is coming from the acid. Alright, so basically this is all the reaction. This is the mechanism involved in this reaction. Now, and so if you have an R group attached to carbon doubly bonded to oxygen, and then you have another R group, this is a ketone. Now you can pause the video and show the mechanism in this reaction. Alright, so again we'll have the hydride H minus coming from the sodium borohydride, which is attacking this carbon, and then we have one of the double bonds breaking, and this is going to give us R prime, and we have O, 3 lone pairs and a negative charge. Then you have your acid coming in, we have the acid coming in, and then the oxygen is going to pick the hydrogen and give you R, C, R prime, and OH. By this time you can tell that this is a secondary alcohol, while the first one is primary. This is a secondary alcohol because the starting material is ketone. So now let's look at lithium aluminium hydride. Now with this reagent, we said that it is a stronger reducing agent than sodium borohydride. Now the only reason for this is that the electronegativity of aluminium is far lesser compared to the hydrogen. So this is a negative charge, and then we have the lithium, which is positively charged. Now let's look at the reaction mechanism involved in this, and I'm going to use methyl benzoate in this. So again we have the benzene ring, Now this time I'm using an ester, so OCH3. So this is methyl benzoate. Methyl benzoate. All right. Now let's look at the mechanism for this. What is going to happen is we have the reducing agent aluminium with the 4 hydrogens attached. All right, so we are going to have an arrow from here to the carbon, and what is going to happen is we are going to form the intermediate, the benzene ring. Then we have the carbon with our carboxide O, 3 lone pairs and a negative charge. Then we have the hydrogen that is attached to the carbonyl carbon, and then we have the methoxide OCH3 attached. Now intermediates are not stable, so when we have something like this, the compound quickly rearranges itself to achieve stability, and so that means that something is going to get kicked off from this. And is it going to be the benzene, the hydrogen, or the methoxide? So what is willing to leave is what we call the leaving group, and then the beta leaving group here is the methoxide. So the negative charge here, 2 of the electrons are going to come down here to form a double bond, resulting in the methoxide leaving. And so what is going to be the product? We are going to have again the benzene ring. Then you have a carbon doubly bonded to oxygen and hydrogen. And you know what this is? This is benzaldehyde. So we are having benzaldehyde, and then we are also going to have methoxide O minus 2 lone pairs. And then we have the CH3. CH3. This is your methoxide. Now what is going to happen again is we are going to have the reducing agent again, aluminium. Remember, it's not only one that we have, there are lots in the system. So we have aluminium, 4 hydrogens attached, and just like we saw earlier, we are now going to reduce this benzaldehyde to give us the alcohol. So again, from here to the carbonyl carbon, and this guy is going to break, and we are going to have carbon alkoxide intermediate, the hydrogen here and hydrogen here. Now this is the time that the acid comes in. So this time we have the acid OH3 plus the oxygen is going to pick a hydrogen or a proton, and this is going to result in the formation of the alcohol, where we have carbon. Now this is the OH, and then the 2 hydrogens attached. All right, so this is the alcohol. It's now a primary alcohol. This is what you call the phenyl methanol, or the common name is benzyl alcohol, phenyl methanol, or benzyl alcohol. So what else are we going to have in the system? Since we have the acid giving us a proton, is going to leave with 2 hydrogens, which means that we can have some water in the system, H2O. Remember, we have methoxide in there, and since finding hydrogen in this system is not a problem, we are going to have the methoxide picking a hydrogen to give us methanol. So we have CH3OH. So we have 2 lone pairs on the oxygen. So that is it. We have benzyl alcohol in the system and a methanol in the system. But then the greater product is going to be the phenyl methanol or the benzyl alcohol. So this is the mechanism involved in this, and I hope this video helps you. Watch out for our next tutorial on the preparation of alcohols. Thank you.